So for 29, it says a crate in the form of a cube with edge lengths of 1.2 meters contains a piece of machinery. The center of mass of the crate and its contents is 3 meters above the geometric center. The crate rests on a ramp that makes an angle theta with the horizontal. As theta is increased from 0, an angle will be reached at which the crate will either tip over or start to slide down a ramp. So not a lot of numbers here. Okay. So A says if the coefficient of static friction is 0.6, does the crate tip or slide, and at what angle does that occur? So let's make ourselves a little drawing here. I'm going to exaggerate the angle drastically just so you can kind of see what's going on. All right, so there's your thing. It's inclined at an angle theta. All right, here's our box. Do you guys agree that if it tips over, this is my pivot point? Right? Okay. So in most of these problems, our goal is we want the object to not rotate, right? And so you can pick any point as the pivot point. There are a couple problems towards the end of this assignment, 28 and 29 are the two that jump out to me, where there's one correct pivot point. Okay? Because we're trying to find the breaking point between rotating and not rotating. So we're still going to set our net torque equal to 0. Follow? And just sort of figure out at what point that occurs. All right? So with that in mind, this is a thing that we haven't talked about. So suppose this, just side note, suppose this thing is real top heavy. If it's top heavy, then my force of gravity is going to land to the right of my pivot point, right? Whereas if it's bottom heavy, then my force of gravity is going to land to the left of my pivot point. Do you guys see the difference in what's happening there torque-wise? Right? For the red one, it's going to tip this way, right? Which is what, clockwise? And for the green one, it's still safe, right? It hasn't tipped over yet. Does that make sense? Okay. So our question is basically, at what point does the torque from gravity exceed, in a, I guess, clockwise direction, exceed the torque from gravity? Did I just say when does the torque of gravity exceed the torque of gravity? Yep. I wish I hadn't said that. All right, so let's see if we can figure out what's going on here. All right, so here's our pivot point. All right, so the problem tells us that the box is 1.2 meters on a side, is that right? So 1.2 meters, 1.2 meters, and it tells us that the center of mass is 0.3 meters above the geometric center. So here's the center. I want to go up 0.3 meters from there. So I'm going to use an X to mark our center of gravity. And draw in my force of gravity. That's going to be mg. And let's make a little note that this distance here would be what, 0.9 meters? Agreed? Okay. So, let's see. All right, so if the coefficient of static friction, mu s, between the ramp and the crate is 0.60, does the crate tip or slide, and at what angle theta does this occur? So I guess there's a couple ways of going about this. Thoughts? What other forces haven't I drawn yet? Normal force and friction, right? Okay, so my normal force is going to occur either just, sort of from the bottom of the crate or at this point, right? So there's going to be a normal force that goes this way. And that normal force is going to be equal to mg cosine theta, right? Do you guys agree with that? Yep. All right, what other forces are you guys? Friction, right? Which way should friction go? Left up the ramp. And again, it should be at that point, right? Follow? So our force of friction static is going to be our coefficient of static friction, which is 0.6 times this normal force, right? So 0.6 mg cosine theta, right? Follow? All right. So the angle is going to increase. So we need to figure out what's going to happen first. Is it going to tip over, or is it going to slide first? So I guess why don't we do this? Why don't we write an expression for the angle at which it tips, write an expression for the angle at which it slides, and then compare the two. Does that seem like a reasonable way to do it? All right. So finding the angle at which it tips is actually just kind of some geometry. Do you guys understand that it will tip once the force of gravity goes to the right of my pivot point?
Yeah.
Does that make sense or no? Okay. Well, I guess we need to figure out at what angle that occurs. Thoughts about how to figure that out? Justin, you got an idea? Does that hand up or?
I guess you probably could, in the sense you know that the bottom half or the bottom part of the triangle is 0.6, and then D is 0.9.
Okay, so you're looking at this little blue triangle that is kind of hiding right here. This guy.
Correct.
Follow? So I think what he's saying is, let's take that triangle and flop it down on its side, and I'll slowly. Whoa, that was a terrible noise. I'm sorry. All right, so this side of the triangle is half of the width, right? So that's 0.6 meters, right? This side of the triangle is 0.9 meters, right? And there's some angle here, right? So what we want to know is, how far do I have to rotate this whole thing before that hypotenuse becomes perfectly vertical, right? Does that make sense? So I want this angle here. Does that make sense, you guys? Or no? Okay, so we can find this blue angle here, right? Because I used theta here, let's call this phi. Everybody cool? Or phi, some people say phi. So phi would be what? The inverse tangent of 0.9 over 0.6. So that gives us some angle. Second tan of 1.5. So that gives you 56.3 degrees. So what do I want theta to be then? Well, how are you getting that though? It's just 90 minus it, right? So 33.7 degrees. So that's the angle at which it will tip over. Does that make sense? All right, so now we need to find the angle at which it slides. Cool? So the angle at which it slides, oh, that's not what I wanted to do. There we go. That was good. I like the Dr. Strange reference. All right. So it's going to slide. Well, you guys tell me. When's it going to slide? What has to be true for it to slide? What?
Equals parallel.
Force of friction equals parallel, right? You've got your parallel component of gravity pulling down the hill. Friction's resisting it, right? So it slides when your force of static friction is less than or equal to, however you want to do that, your Fg parallel, right? So let's see, our force of static friction, we already said that was 0.6 mg cosine theta. Fg parallel is mg times sine of theta. Let's see, the mg's cancel. Divide both sides by cosine, and you get 0.6 equals, what sine over cosine? Tangent. So our theta is going to be, thank you, 0.6. 30, yeah, basically 31 degrees, right? So it slides at 31 degrees and it doesn't tip until 33 degrees. Follow? Yep. Questions with that, you guys? All right, this is my honors sheet. All right, and then in part B, you're increasing your force of static friction, right? So that means that your angle is going to get steeper before it slides, right? So it's going to increase this 0.6 becomes 0.7, and so this angle ends up being more than the 33 degrees, and so it'll tip over first. Make sense, you guys?
Yes.
All right. The reason I wanted to do this was I felt like this was not a thing we had talked about before, about when it tips over. Did my train of thought there make sense, you guys, that it tips over once that force of gravity goes past your pivot point?
Yes. So this green triangle that you have highlighted,
Yeah.
that's just in the box. That's just that.
Correct.
That's not the parallel force of gravity. Or I mean the perpendicular. That's not the vertical line that you have there. That's mg.
Correct.
Right. Okay.
Right. Well, but at the point where it tips over, the hypotenuse of that triangle you're talking about is parallel with the FG, right? Because that's the breaking point.
But it's not the same line. What I'm saying is there's this green line, the
The-
hypotenuse of the green triangle, and then you have your FG line.
Those are two different lines.
Different line.
The green one is a distance triangle. The highlighter green one is a distance triangle, and the force is a force. So, cool?
Yep.
Good, you guys? All right. So to me, that seems like a good one. Sarah, you were asking about the rock climber hanging on the wall one? The other rock climber one, the simpler rock climber one? What number is it? The number 23, the one that says that doesn't look safe? Can we pause through that real quick, you guys? Is that all right?
You can do.
I think we can do it. We got 3 minutes. We'll at least set it up.